In this video, we'll be seeing about flex sensor. A flex sensor, also known as a bend sensor, is a low-cost and easy-to-use sensor which is specifically designed to measure the amount of deflection or the bending angle. This became popular in the 90s because of its use in the Nintendo Power Gloves. Now it is used to determine joint movement, a door sensor, a bumper switch for wall detection, or a pressure sensor on robotic grippers. A flex sensor is basically a variable resistor that varies in resistance upon bending. Since the resistance is directly proportional to the amount of bending, it is often called as a flexible potentiometer. Flex sensors are available in two sizes. One is the 2.2-inch flex sensor and the other is a 4.5-inch flex sensor. Next, we'll see about the construction of a flex sensor. So, a flex sensor consists of a phenolic resin substrate. That is, this brown color layer is a phenolic resin substrate upon which a conductive ink will be deposited, which is a black color layer. And upon this upon this conductive ink, a segmented conductor is placed, which is a white color. This is the segmented conductor. This is placed on top to form a flexible potentiometer in which the resistance changes upon deflection. And one important thing to note in flex sensor is that it should be bent only in one direction, that is away from the ink, opposite to the ink. If we bend it in the other direction, then there are chances that the flex sensor may be damaged. Next, we'll see how the flex sensor works. The conductive ink printed on the flex sensor acts like a resistor. So when the sensor is straight, that is when the sensor is flat, the resistance will be about 25 kilo ohm. And when the sensor is bent about 45 degree, it will be 62.45 kilo ohm, and for 90-degree bend, it will be 100 kilo ohm. When the sensor is bent, conductive layer is stretched. This will result in a reduced cross section. So this reduced cross section results in an increased resistance. Next, we'll see how to connect a flex sensor and how to read the values from a flex sensor. So consider this as a flex sensor. The flex sensor will have two pins. One pin will be connected to the power supply, which is normally 5 volt or 3.3 volt, and the other pin will be connected to a pull down resistor. Here, normally we use a 47 kilo ohm resistor, and the point between the flex sensor and this pull down resistor will be connected to analog voltage. That is, it will be connected to the ADC input. So when we connect the pull down resistor, it becomes like a voltage divider. So and when we connect this analog voltage, we create a variable voltage output which can be read by the ADC input. And one thing to notice that the output voltage we measure is the voltage drop across the pull down resistor and not across the flex sensor. So the output of the voltage divider configuration is described by this equation, that is V0. V0 is the output voltage. V0 is equal to VCC into R by R plus R flex. So VCC is the power supply, normally 5 volt for Arduino and 3.3 volt in the case of Node MCU, and R is the resistor we have used. In this case, it is 47 kilo ohm, and R flex is the resistance of the flex sensor. That is how much resistance it gives. It varies for each bending angle. Next, we'll see about the circuit connections of a flex sensor with an Arduino. So, as I already said, a flex sensor has two pins. One pin of the flex sensor will be connected to the power supply. Here, in the case of Arduino, it is 5 volts. So, one pin is connected to power supply, and the other pin is connected to the pull down resistor, that is the 47 kilo ohm resistor, and that will be connected to ground. And the point between the flex sensor and this pull down resistor, that is this point, will be connected to A0, which is the ADC input of Arduino. Next, we'll move on to the code. First, we declare and initialize certain values. First is the flex pin is initialized to A0. From A0 only we read the flex values. So we give flex pin as A0. VCC is given as 3.3 for node in the case of node MCU. If it's Arduino, we'll be giving VCC as 5. And RDIV is the resistor used. Here we have used a 47 kilo ohm resistor. So RDIV is given as 47,000. And next is the flat resistance and bend resistance, which is the minimum and maximum value of the flex sensor. That is when the flex sensor is flat, or if it's at 90 degree, which is 25,000 and 100,000 respectively. Next, in the setup function, we initialize the serial communication, and we have initialized the flex pin as the input pin. Next, in the loop function, first we read the flex pin value, and that is stored in the ADC flex. Next, when the Arduino converts this analog voltage into digital, it actually converts it to a 10-bit number of range 0 to 1023. So to calculate the actual output voltage, we use this formula ADC flex into VCC by 1023. From that we'll get the V flex value. And next we calculate the resistance of the flex sensor using the formula from the voltage divider equation. And that is what we have given here, that is R div into VCC by V flex minus 1, and this will print, this resistance value will be printing in the serial monitor. Finally, we use this calculated resistance value to estimate the sensor's bend angle. To do this, we use the built-in function called map function. So in this map function, we have given the R flex value, flat resistance and bend resistance value. So from this, it will map and it will print the angle. Here we have given the print function, so it will print the angle value in the serial monitor. This is the output for the code we saw. So in this we have printed the resistance and the bend angle. So as we can see, first when the resistance is about 37,000 ohms, the bend angle is 0 degrees, and as the resistance increases to 39,000 and lastly to 93,000, the bend angle also increases from 0 degrees to 90 degrees. First, we have connected the flex sensor to a multimeter to see the resistance values of the flex sensor. So as we already saw, when in straight position, the resistance of the flex sensor is about 25 kilo ohm, and here even though we don't get a very accurate value, we get a near value, that is 37 kilo ohm. And when bent, the resistance increases. Here we can see that the resistance increases and the maximum resistance at 90-degree angle is about 90 kilo ohm. When we release the flex sensor, it comes back to its original value. Here we have connected the flex sensor to a Node MCU board. The flex sensor has two pins, and here we have used a 2.2-inch flex sensor. In this, the left side pin will be connected to the conductive ink. So this left pin of the flex sensor will be connected to the Node MCU's 3.3 volt. That is the Node MCU's power supply, which is 3.3 volt. And the right pin of the flex sensor is connected to a pull down resistor. Here we have used a 47 kilo ohm resistor, and that will be connected to ground. The point between this pull down resistor and the flex sensor will be connected to A0, which is an analog input of the Node MCU. So from this point only, we will see the values, that is the resistance values of the flex sensor. Next, we will see how the resistance increases as we bend the flex sensor. That is, the resistance will increase as the angle of the flex sensor increases. I have already uploaded the code in Node MCU. Now the flex sensor is in almost straight position. We will see the output results for this. Here as we can see, the resistance is reads about 36,000 ohms, and for this bend angle is 13 degrees, which is almost a straight position. Now I'll bend the flex sensor. As I already said, the sensor has to be bent only in one side, that is away from this conductive ink. I have bent the flex sensor. So as we can see, the resistance increases, that is it comes to about 90,000 ohms, and for this resistance the bend angle calculated is 77 degrees, and we can see that I have bent it up to that amount of degrees. If I bend it more, it comes to about 90 degrees, and the resistance also comes nearly to 100 kilo ohms, which was what we already saw. Now if I leave the flex sensor, it comes back to its original position, and that is 13 degrees.